Thank you very much. We are going to talk right now about one use case we developed last year mainly. First, I will try to put some context to understand the complexity of the use case, and then I will pass the key to my colleagues from Cisco that was the one that has done the hard work. First, trying to explain the issue. The issue we have is there are some agreements between the telecom operators for the radio access network. As it's not feasible to deploy the radio access network everywhere because there are too many sites. Normally, there are agreements between operators to use the radio nodes of other operator for our own services, and in the opposite is the same. So, to securitize the own traffic in other RAN, normally there is a securitization of that traffic. Then the other operator opens an IPsec tunnel from the radio node to a device in our network that is the security gateway that centralizes all that IPsec tunnels. In that process, there was a lot of manual things that has to be done in our part, just in the part of the security gateway. These are Juniper devices mainly, and for the Orange radio, for our own radio, we don't have the need to securitize that traffic because it's in our own network. Okay. We started developing a use case to automatize all the processes to configure the security gateways. We started with a service to create that tunnel, that the IPsec tunnel, just in our part, but it was not enough because there are many people touching the same devices, changing things, and even doing that through NSO. There are a lot of conflicts to do that. When one person do a sync from, other person try to commit and then breaks the transaction of the one. So it was a nightmare. That's why we create some actions on top of that service to simplify that operations. And we started doing the package to create that manage all that creation, another to delete, to simplify the deletion, and to manage that conflicts. But as sometimes there are many tunnels that has to be managed at the same time, it was not enough because of the time. So we create new services to create many or delete many things at the same time and reduce the time consumed for that. That made us a very complex use case with many elements all working inside NSO, but needs to be very tight together. Okay. When we thought that we have almost everything considered and everyone was using NSO to do every operations completely smoothly, very well, we found a new need for 5G due to some regulator rules and some security rules. There has been a mandatory process to securitize also our own RAN, our own radio access network. That means we need to touch tens of thousands of elements in a very short time, very smoothly, in a multi-vendor environment, and with no knowledge at all about how to do that in that elements. So this pushed us a lot because we thought that the process was very clear, but right now the new element was a very uncertainty. Analyzing that new requirement, we get a strategic context And we see that this makes us to make a technology evolution. We are forced to do that, and we need to evolve, and the technology we have right now is not enough to fulfill these requirements. Also, we need to scale, because we cannot do one by one. If we the securitization one by one for tens of thousands of elements, it can take years to be done. It must be reliable. We have millions of customers, of mobile customers, that use that radio. We cannot make an outage when we do these operations. And it's very, very difficult to do. So automatize that and keep the security of that automatization is mandatory. SWOT analysis. Weakness and threats we found in that process. We don't have technical information about that. Only the vendors of the radio nodes knows about how to configure that elements, and they don't want to share that information. So we start with a blank page, and no one telling us how to fill that page. That's why there's a lack of nets. There's no driver to perform that actions into the elements. Threats. First, the massive executions. Okay, if we touch many radio nodes at the same time, maybe we can provoke a black hole and we can go to the news. We don't want that. And all the confidence we have won doing the other part of the automatization can be lost if we fail doing that. If we provoke a black hole, that it doesn't matter how well we have done before. This is a problem. But it's also we have a strength, and it gives us opportunities doing that. The main strength is we have successfully configured all the security gateways. So we know how this process runs. The only missed information is the way to do that in the radio node. But the other part and all the different end-to-end processes that are involved are well known by us. So it's one strength for to begin this process. And also, if we success in that part, we will go beyond the IP domain doing the automation with NSO. That is a very, very, very good point. The opportunity is, okay, this is the first use case. If we succeed doing the first use case, maybe there could be another use cases touching the radio access network with NSO. And also, well, there's an innovation opportunity to do that. The plan to do that that process. First, find the collaboration of the suppliers. We haven't that collaboration directly from the vendors, so we found a partner that knows also that vendor processes and that vendor configuration to help us fill in that blank page we had before. Also, the internal tools development. We have the tools, but the tools have a hole to fill. We have a net. Also, this must scale. So we need to think about how this net or pseudo net will perform to ensure that everything will work as we expect. So it's not just put that comments and forget. Also, it will have visibility. And we need to push that visibility internal, if we success, to see that, okay, we are able to do that. Trust in me, now and later on. And also, all this process must push our leadership in automation into the company. Okay. So taking this, we pass the key to Jose to explain how we did it.
Okay, thank you, Luis. Okay, I want to start my presentation just asking, I'm doing a survey here. How many of you have been working with NSO managing more than 50 devices? Just don't be shy. 50 devices is okay. And more than 500 devices? Okay, same number. More than 1,000 devices? Okay. And more than 5,000 devices? 5,000 devices. Okay, good. Okay, it's a main. Okay, so what would you do if you were asked to configure 10,000 Ericsson and Huawei radio nodes with not a single net available? Okay, it was really challenging because we didn't know how to do it or what to do at that time. Okay, but as good engineer knows, the biggest challenges are the ones that drive us the most, and these are the value, what really creates the value, right? So when Luis put these challenges on our table, there were three burning questions here. First one is, how can we uncover the data model of the radio nodes with no information? The vendors were very reluctant to provide this information. The second one is, how can we configure thousands of complex and diverse nodes? And above all, how can we pull it off in a record time? Okay, we will see that later. The thing is that we say, okay, we accept the challenge, and actually we came with a solution that it's not only scalable, it's also efficient, and most surprisingly, it's quite elegant, to be honest. Okay, so we have. Okay, we are here just to show how we turn this challenge into something that works. And looking back now, I think we have like 6 major challenges that we want to share with you. Okay. Okay. The first one is discover the radio data model. Before doing any kind of automation, we have to crack the radio node's logical DNA. And for me, it was like a black box, tasking with managing and controlling the radio nodes, but with not information at all. We have only a few CLI commands templates provided by a partner. That's it. Okay, so how could we start working with that? And the answer is just, the first step was uncovering the logical framework, the data model, that the base station controller, which is the software element that controls the radio nodes, relies on to supervise and configure the radio nodes. Okay, that was the first step. So I see the data model as a map, not of physical hardware, but logical building blocks inside the radio. And at the core of this map, there are, I'm going to use terminology in Ericsson, which is the managed objects. Okay, and these are dealing with specific hardware and software components. So the base station controller somehow manages these components, and we have to send commands to the base station controller just to do the changes or perform or create these managed objects. Okay. But here is the twist. We have no manuals, no diagram, nothing. We were blind. So how did we solve it? We just became a kind of Indiana Jones, trying to do a digital archaeologist. And what we did is just reverse engineering. That was the trick. With that information, reverse engineering, we analyzed per vendor 50 CLI commands, okay, hunting for 20 to 25 managed objects. And piece by piece, we could reconstruct the whole parent-child hierarchy, okay? And finally, we could end up with a data model that was workable, let's say, okay? So that was our step. The challenge number 2, we have to guarantee the managed object hierarchy. If you see MO, it's managed objects, okay? So once we have the structure of the relationship between parent and child in between the MOs, then the next step was to prevent that the child was not configured or created before the parents. For example, you cannot assign an IP address to an interface if you don't have the interface first, right? It's the same thing. So if you see a structure, parent is the interface, the child is the IP address. So we have to prevent that. That was our mission. So for that, we developed an algorithm, okay, that what it does is we take the list of commands that creates the manage objects, we scan it, and we sorted them. So we could ensure that the children were created after the parents. Okay, that was the key. And that was, let's say, the secret source of our net emulator somehow. Get an order list of commands and put them or sort them out to have a clear vision that we are not going to break anything, okay? To keep or guarantee the system integrity. Okay, step number 3. We wanted to be as more efficient as possible. Okay, so for that we thought of our pseudonet or net emulator. I will call it net emulator to just send the commands that was required. So in the previous step we have the list of commands, order list of commands, and now we wanted to apply some rules saying, okay, if the manage object is already in the radio node, I'm going to remove the command that created. It doesn't make sense to send the command, right? If the MO doesn't exist, okay, it is keeping in the list. And if it is already created, but the parameters are not exactly the same, then we stop. We are not going to send it. It was a requirement from MasOrange, okay? So that gave us a kind of, we optimize the execution, we reduce errors, and we accelerate large-scale deployments. Okay, remember, 10,000 devices. Okay. Okay, challenge number 4. Okay, when it is come to automate at scale, having a complex solution that it is a nightmare to add one more piece, one more managed object, doesn't make sense. Okay, so from the very beginning, we have clear that our net emulator should be simple and easy to upgrade. Okay? And so for that, what we did is to have a kind of catalog. When we have a new CLI command that we want to enter, a new MO, we put it in the catalog and just refer who is my parent and who is my children's, if there are any. Okay? Just with that information, very simple. And the algorithm we did in the step number 2 takes that information, takes the data model that we build in the step number 1, and we don't need any reconciliation, any recompilation. We don't need to modify the core logic, and we avoid also massive regression tests. Okay, so that was the key, basically. Okay, challenge number 5. Remember, we have 6. Challenge number 5 is that the communication, NSO communicates with the radio node, but it is not a direct connection. It is done through a radio network manager. Okay, so NSO, our net emulator, talks with this radio network manager, and the radio network manager talks to the radio nodes. Okay. So here was the trick. We have no visibility of what was happening and when it was happening. And we have a high dependency on the radio network manager, communication between the radio network manager and the radio nodes. Okay, so for example, if we issue a reboot command, okay, so the NSO didn't know exactly at real time what was happening, okay, what's going on in the radio, and we have to wait for the radio network manager to communicate with the NSO. So probably the radio node was back online several minutes ago, right? So we have to provide a kind of mechanism to pull the radio node. Okay, what is going on? Are you up or not? Okay, to go on with the workflow in the NSO. Okay, and this was the most challenging one and the biggest requirement. Just, we have a massive number of devices, and we have a lot of configuration to be done, okay? And the thing is, okay, let's break it down to an example. We have 10,000 devices. We have to do it in 2 months, okay? All this IPsec tunnel configuration has to be done in 2 months. We have 20 days per month, let's say, workable days, and each maintenance window is 8 hours. So we need to configure 250 devices per night. And each process takes between 8 and 15 minutes. For instance, if you want the commands that you send to a radio node from Ericsson to take effect, you have to reboot the radio node. And it takes between 8 and 15 minutes. Okay? So as you can imagine, maximum parallelism is not important, it's critical. If you cannot make it, it doesn't matter. If it can't be very elegant, but it doesn't work for MasOrange, okay? So we end up with this architecture. I will be very quick on this one because Juan Luis will explain. But as I said, this is not a net. This is a net emulator, okay? And basically it's an NSO action with 3 operations. One is just to configure these managed objects. Another one is to send the live commands. For example, if I want to reboot the node or just check the alarms or whatever, I will use the command live operation. And the third one, which is a bug here, a typo, is set command, if I want to modify something that already exists. Okay? Simply, it's an NSO action, and on top of that, I can use any NSO service. For instance, IPsec tunnel is a service to configure. So I can have, in the future, more NSO services using this net emulator because I have these operations available. In the future, we plan to have also the delete operation, okay? But so far, we have configured these ones. And the NSO action, the net emulator, will talk with the radio network managers, okay? So all the operations are done on the radio nodes. This is the architecture, and now I will pass the ball to my colleague, Juan Luis.
Thank you, Jose. Okay, we can keep this one, or let's move to the next one. This is basically the same end-to-end architecture that Jose was showing, but just left to right. So we have the 3 elements, right? The radio node manager is just a third-party element, so we don't care about that one. We have the NSO service, and then what we call the net emulator, which we will go deeper into this one. For the NSO service, just what I want to highlight is that this is the one receiving the user intent, so this is the one that has the service model, let's say, of the configurations we want to do. It is a service package, but actually it is not implemented as a normal service, right? Because it will not end up applying a template and letting the fastmap calculate the diff set. What it will do, it will calculate internally a list of commands that have to be configured on the radio node manager, and it will pass those commands to the net emulator action, right? So even if it is a service package, internally it implements a more or less complex flow with some pre-checks and commands calculation, and it will finally call the actions, the action points on the net emulator to send the commands and to wait for the response and maybe do some post-checks, abort the transaction or whatever. However, it was important for us that it is a service because we want to keep track of the services instance that we create. The key for the service is the name of the radio node, even if those are not real NSO devices, let's say, because as we said, we don't have a net, so we don't have a device model for them. But we wanted to keep track of that also for the visibility that Luis was mentioning, right? It is important to be able to expose some KPI about how many nodes we are configuring per night, etc. For the net emulator, I think we will go straight away to the next slide where we explain a bit better the architecture. First of all, it is an action package, pure action package with 3 action points. If you see the graphical representation of the Young model, they are very simple action points. They only have as inputs the name of the node where you want to execute. This node is actually the radio manager, so not the radio node itself, but the manager who is finally configuring that node. And then for the live command, this is for operational commands, right? So it will receive as an input the string for the command. It will wait for the radio node manager to execute that command and to give a response, and it will send upwards the raw output message of that is given back by the node manager. Of course, we can raise some errors or result Boolean variables, etc. The configure one is a bit more, it's for configuration commands, and it accepts not a single command, but a full list of commands, unordered commands. So there is where we come in with this process for the net to be able to reorder, and we will go a bit deeper now into that. So again, it will give the result of all the configuration that is done by the radio node upwards. And the set is a bit of a, let's say, a special case of the configuration. It accepts one single configuration, and it is aimed to change the value for a managed object that is already created in the node. So these are our 3 actions. And then we came up for this architecture for the, let's say, net emulator. You have to remember that actually we developed this for 2 different vendors, so we wanted to come with an architecture that can be, let's say, reused between the different vendors, and that if in the future we have a new one, we can reuse part of the modules and just develop some specific ones. So we came up with this 3-layer architecture. On the top we have, let's say, the input, the northbound part of the action, which is the one that we presented before. Obviously, we did this to be used by the NSO services, but naturally, this action, this net emulator, is now exposed in the NSO CLI and in the RESTconf API, so it means that if any other use case needs to send a live command or some configurations to the radio managers, it can just invoke those 3 operations. Then we have a middle layer, let's say, where we have the different logic. So the 3 main elements that, the 2 elements that Jose was mentioning, the command optimizer, let's say, being able to decide if we have to send all those commands that we get in the input or we can skip some of them. The command sorter, so based on that logic of understanding how the model works and being able to order the commands by the hierarchy. And finally, the response parser, right? This is purely, let's say, we need to understand the syntax of the responses from the radio node manager. And then finally, we have some communication handler. This is a, net emulator also in the sense that it is handling the communication to the final network element. So here we put like 2 different modules. On one side, we have, let's say, the credentials. And for that, we actually leverage some other NSO package where we basically use NSO to store a list of encrypted credentials, usernames, endpoints, etc. We use that not only for this action or for this service, but also for the workflow managers to be able to, let's say, use it as a vault for encrypted passwords. And then the communication handler, which is basically handling all the session and connections to the endpoint. Out of the 2 vendors, here we implemented 2 different things. One of the vendors was purely REST API, so we use the Python requests library, and we, the usual token management, opening connections, etc. For the second vendor, it is a terminal type of connection, and what they did is they provide a Python library themselves that you can import and use to open a terminal, send command, expect for the responses, parse the response, etc. Here in the architecture, we kind of we wanted to mark the ones that are very tied to the vendor and the ones that are fully reusable. So actually, from the 2 actions or the 2 packages that we developed for each vendor, those 4, the 3 on the top and the credentials handler, are totally common for both of them, but the others obviously depend on the syntax and the hierarchy of each vendor. Okay, and now we are just going to briefly show the internal flow of the 3 operations that we implemented. These two are the most simple. So the command life is purely operational command. We just go to the, let's say, to the communication handler, and here the colors try to match the colors in the architecture. So just as a recap, right, the blue ones is the top level, green ones is the internal logic, and orange one is the communication. So here basically we have to, get the credentials, wherever it is stored, we open the session, send the command, wait for the response, and pass that upwards. We don't do any processing on that, right? We just rely on the upper layer to understand what is the output of the command that they are trying to execute. Then for the set, we already start doing some optimization. So first, remember that this is a configuration command, so we have the internal logic to understand which command, which get command is equivalent to the set. So we open the connection to the radio manager, we get the configuration that we want to understand if we want to modify or not. We compare the current config with the configuration that is being input to the action. And then based on some logic, if the configuration is the same, we don't need to really configure it. Or if it is different in some non-permitted type of logic, we just raise an error and respond back. But if we decide that we are able to set this new value, we just go to the communication layer again, open the session or connection, and we configure that and wait for the response and give a pass response if it was successful or not. And finally, this is more like the configure one. Remember here we had not a single command, but a full list of commands. So we have to go through this entire process of optimizing the commands. And for that, we have like a recursive process in which we calculate the equivalent get commands for all the configuration commands. We get that configuration in an optimized way from the radio manager. And then we do this comparison in the manage objects, trying to decide which ones we can configure, which ones we actually don't need to configure. Or as Jose said, if something is really not configurable at that point, we can just raise an error. But let's assume we got 50 commands as an input. We decide that out of those 50 commands, we only need to configure 20. So we come up with an optimized list of 20 commands. Then we go to the sorting process, and this is based, as Jose explained, on the hierarchy that the net emulator knows of how to configure the top level first and then the children of that top level. And then we just go through the communications, send the full list of commands, wait for the radio node manager to act to configure the actual radio node, and then parse all the response back, right? So if you see, as Jose said, it's not very complex in the architecture or in the flow. It's kind of elegant solution. And we think it's also quite reusable, right? So that's also why we wanted to present here. Maybe this just rings the bell for someone else to use this type of actions whenever the net is not available and it's not really possible to develop, right? Because either it's not a, let's say, very global use case, or there are no possibilities to access the final devices or for the BU to do this reverse engineering or this work that they normally do with the nets. And with that, just a brief wrap-up. So here we were able to implement our use cases based on technologies that were until now completely out of the scope of the NSO in MasOrange. So it was, the radio part was always like a very different domain. Nobody was really configuring that, and we were able to implement and to bring that into the automation domain in MasOrange. As a lesson learned, of course, you always need to grab someone that knows how that works. If you don't have the information, you need to find a partner, or you have to partner with other companies or with someone in-house that really knows the technology. And then as next steps, probably this is maybe in the roadmap, not sure if it is now when it will trigger, but probably we have to start implementing some delete operations. Until now, the requirement was mainly for the configuration, which was the regulatory requirement. So, but if we have to implement the delete, with our architecture, it will come very naturally, right? How we implement it. And I think that's it. So we give the floor for questions.
We have Slido open. You can ask questions on Slido or just raise your hand and I will pass you the mic.
Maybe you said it, but I will ask again. What protocols was used to communicate between NSO and the network device manager?
So one of them was REST. So one supported the REST API. The other one, to be honest, I don't know exactly underlying because it's some kind of, they say terminal, so it's kind of SSH, I guess, in the background, but they offered a library, Python library. So really you don't need to do all the programmatic thing. You just use the functions that they provide, right? So I think I remember functions like open terminal, open session on top of that terminal, close, etc. Yeah. So it's kind of...
That is for Ericsson, for Huawei's RESTCOM. Oh, sorry, REST API.
Okay.
Exactly.
And the second question, I was wondering, does NSO has the devices configured on NSO was the radio node manager or the radio nodes themselves?
Actually,
No, they are not in NSO as devices itself.
Yeah.
As we have the name of the radio nodes in the other developments we have done before as a tunnel. Okay, we keep that service structure to keep the name of the radio node. So it exists as a service instance, but not as a device.
Yeah.
Okay.
It is just a string for us, right? This is the name of the device. It's a string, but it doesn't have a device model on the NSO.
Okay. Thank you.
Thank you.
We have one question from Slido. Why did you choose a net emulator over a generic net?
Because there is no generic net. And there is no possibility to do it due to the restrictions of the information we had.
Yeah, remember, we only have a set of CLI command templates. That's it. And from there, we have to do reverse engineering to figure out the data model. Okay, so that was the first step. It was really tough to do. So building a net, as we usually know, it was really very difficult.
Yeah, if I may add on that, also I think by the experience in the team, let's say development team, for us it was more natural or more, let's say, easy or time due to the time constraints as well to build something based on Python package rather than start playing with a generic net, right? Which we don't have the experience in the team.
We have any more questions from the audience? All right, thank you very much.
Thank you.
Thank you, Anna.
Thank you.
Thank you, everyone.